We now define the Lebesgue integral of simple functions. But first, what do we mean by a simple function? A measurable function say phi from x into r is called simple if the range, so this is the set of all values of phi, is finite. So again, a simple function is a measurable function having a finite range. In this way, we can write the simple function with the so-called canonical representation as follows. So here, phi is the sum. So it is a linear combination of characteristic functions where the coefficients, say alpha, belong to the range of phi, and the characteristic functions are taken with respect to the inverse images of the singleton consisting of the image alpha. Now here, use the following notation. So we remove the parentheses for this inverse image of a singleton for simplicity. So again, note that this characteristic function evaluated at x is either 0 or 1. So it is 1 if x is in phi inverse of alpha. In other words, if phi of x is an element of this set, since this set consists of only one element, so therefore this is equivalent to saying that phi of x is in alpha. So if that's the case, the value is 1. Otherwise, it is 0. Now, since phi is a function, so if alpha is distinct from beta, then the inverse images associated with these numbers, alpha and beta, are disjoint. So for different values in the range, these sets are pairwise disjoint. Okay, so let us have some annotation. We denote by S of x sigma. So here, sigma is the sigma algebra on X. So this is the set of all simple functions from X into R. And we consider the subset S plus to be the set of simple functions from X into R that is non-negative. we now define the Lebesgue integral Lebesgue integral of a non-negative simple function as follows. So we will denote the Lebesgue integral by this notation. So mu is the measure on x. So this is defined to be the sum taken over all alpha in the image of phi. So this is alpha times mu phi inverse of alpha. And with the convention that well, it's possible that alpha is 0. So here, if this is 0 and the measure is infinite, then we set the product 0 times infinity to be 0. And with this convention, this is the same as the sum taken all images except 0 of this product. So the idea here is that this is somewhat your height. And this is your base. And this convention is explained in the following example. So suppose, let's say, I have this simple function phi from R to R. So here we take the Lebesgue measure in R, the one-dimensional Lebesgue measure. And it is defined as follows, let's say, phi of x is 1 if x is between a and b, with a less than b, and 0 otherwise. So clearly, one can show that this is measurable. Indeed. You can take the inverse image, let's say, of a subset E. This one is either the singleton 0, the singleton 1, the set containing 0, 1. It should be in the domain. So the inverse image is either, let's say, the closed interval AB, the complement, or the empty set, or R. Well, depending on whether 1 is in E Okay, so it's better to write this in the following way. So again, inverse image of E is either the closed interval AB if 1 is in E and 0 is not in E, it is the empty set, or it is the complement if 0 is in E and 1 is not in E. If both of them are in E, then you get the whole set of real numbers, and you get the empty set if neither of the two is in E. So in any case, these are all Borel sets for any. In fact, E, which is a subset of R. Alternatively, you can recognize that this function phi has the following canonical representation. So it is the characteristic function of the closed interval AB. So this is measurable since the closed interval AB is measurable. Okay, so this is a measurable function, and since it has only two values, it is 1 or 0. It is 1 or 0. So we can calculate the integral in two ways, provided by these two formulas. Take note that for the first, since these are only the values of phi, so and then we take the Lebesgue measure, lambda, of the inverse image of the singleton alpha. So this is equal to, let's say, 0 times the, so when alpha is 0, so 0 times the Lebesgue measure of, so if alpha is 0, you are in this case. So with that, we get this interval plus when alpha is 1, you get this case. So here we have 0 times, take note that this has an infinite measure, and the measure of this closed cell is just the difference. So this would be B minus A. So we're telling here that we can ignore this part. So if the value is 0, even if the Lebesgue measure is infinite, we define the product to be 0. Well, this is consistent with our geometrical intuition that, let's say, this is your simple function, and this one has a height 1. From A to B. and otherwise it is 0. So if the height is 1, again, the geometric interpretation of the area, or the integral, I should say, is the area, since we have a non-negative function. And obviously the area here would be b minus a, since the height is 1. So here we have alpha equals 1. The height in here, we have alpha equals 0 and alpha equals 0. So if the value is 0, you have no contribution on the area. So that's why we can ignore this term where the image is 0. And in other words, this is the same as the sum. Well, this is only a single term. With respect to the non-zero value, by ignoring the case alpha equals 0. So that's the justification of this convention. 0 times infinity is 0. Okay, so if we have this integral, then some remarks. Note that the first, the Lebesgue integral of a simple function, a non-negative simple function, is also non-negative. And it is moreover, it is infinite if and only if there exists a non-zero alpha in the range such that the measure of the inverse image is infinite. The second, we can also define the Lebesgue integral of a simple function, not necessarily non-negative, as follows. So the Lebesgue integral of this is also defined, well, following the definition. So we have the same definition. However, there should be a warning. So provided that the operation infinity minus infinity will not occur. So that is it is possible that we have, let's say, a negative alpha, and the measure of the inverse image would be infinity. So you will have negative infinity in that case. So this operation is not well defined. So we, in fact, one can construct examples wherein this is not well defined. So we would like to remove this case. So the integral of a simple function, general a simple function can be defined analogously as long as this operation infinity minus infinity will not occur. So there are some nuisance here for general simple functions. Okay, but if you go back to our procedure last time, the next step, so going back to that part, our next step would be the case of non-negative measurable functions. So it would be natural only to discuss the properties of the Lebesgue integral for non-negative simple functions. And with that, we restrict the study to this definition. Okay, so before going to some properties, let us provide an alternative formulation, a more friendly representation. So suppose I have a simple function, a non-negative simple function, wherein the values are enumerated. Suppose that this simple function has n distinct values, and let us define a sub j to be phi inverse of alpha sub j for j from 1 to n. And in this case, they are pairwise disjoint. These sets are pairwise disjoint for different indices due to the assumption that the alpha sub i's or alpha sub j's are distinct. And in this way, the canonical representation of your simple function can be written as follows. So it is the linear combination. So this is the sum from j1 to n of alpha sub j times the characteristic function of a sub j. And in this way, the Lebesgue integral can be also written as follows. So this is the same sum, same coefficients alpha j, but instead we take the measure of a sub j. Okay, so this is a friendlier, as I said, a friendlier representation for the simple function and the Lebesgue integral. So we enumerate the distinct values of the range. Now, going back to the Dirichlet function, so the canonical representation of your Dirichlet function say f is the characteristic function of the closed interval 0,1 intersection with q. So this is already in canonical form. Therefore, and it is simple because this is countable, hence it is measurable, Borel measurable. Because a countable A set can be written as a countable union of singletons, since singletons are closed, and closed sets are Borel sets. Therefore, countable sets is the countable union of closed sets, therefore measurable. Borel measurable, to be precise. And with this canonical representation, here lambda is the one-dimensional Lebesgue measure. So the Lebesgue integral of this simple function. So the Dirichlet function is a simple function because it is measurable. It is the characteristic function of a measurable set. So it is simple, and according to our definition of the Lebesgue integral for the simple function, this is you take all non-zero values. In particular, there's only one. That's 1 times the one-dimensional Lebesgue measure of the inverse image. This is the set of rationals in the closed interval 0 to 1. You can show that the Lebesgue integral of a countable set is 0. So this Lebesgue measure is 0. So therefore, this is 0. So the Lebesgue integral of the Dirichlet function, viewed as a simple function, is 0. So in this case, Dirichlet function is Lebesgue integrable. So take note here. So we have a very simple definition of the Lebesgue of an integral. Okay, and with this, we can now integrate the Dirichlet function. And this also tells us that the Lebesgue integral is equal to 0. Well, the idea here is that your Dirichlet function is equal to the constant function 0 except on the rationals. But the set of rationals in the closed interval 0 to 1 being countable as Lebesgue measure 0. So you can think of this as the 0 function and then choosing countably many points and then redefining that function to be 1, to be 0, or yes, to be 1, I should say. And in that case, you do not affect the overall integral that is 0. So as I said, this is 0 to 1. So Dirichlet function is almost the constant 0 function. However, if you have, let's say, a rational Q, you change the definition into 1. So the height here is 1. So you do this countably many times. And since a single point here does not contribute to, does not alter the area, which is 0, the Lebesgue integral is 0 in this case. So that's somehow the intuition why the Lebesgue integral of the Dirichlet function is 0. So as another example, let us define the following simple function phi. So it is 3 on the closed interval 0 to 1. So that would be, say this is 0, 1, 2, 3. So the value is 3, this interval. And on the open interval 1 to 3, it is 2. not including 1. So that would be the graph. Take note that this is already in canonical form. So therefore, we can use this to get the Lebesgue integral over R. So outside, your function is 0. Okay. Outside the closed interval 0 to 3, your function is 0. So the Lebesgue integral with respect to the one-dimensional Lebesgue measure of this simple function is given by 3 times the Lebesgue measure of the closed interval plus 2 times the Lebesgue measure of the open interval 1, 3. And this is 3 times 1 plus 2 times 2, and this is 7. And this is the geometrically the area of this shaded region here. Okay, so let us consider the following observation. We can also write this simple function phi as follows. So we retain the first characteristic function, but then we split the half open, half closed interval 1, 3 as follows. So the first one is the interval 1, 2, and the other one is the interval 2, 3. So take note that this is not canonical, since the coefficients are not distinct. Although the sets involved here are pairwise disjoint. So again, not distinct due to this fact here. Okay. However, what if we apply this representation as if it is canonical? So in other words, what if I use this representation to calculate the Lebesgue integral of phi? So here we will have 3 times the Lebesgue measure of the closed interval 0 to 1 plus 2 times the Lebesgue measure of the cell 1, 2 plus 2 times the Lebesgue measure of the cell 2, 3. So calculation leads to the following, which is equal to 7. So here, even though we partitioned the second characteristic function into 2 parts, where the parts are pairwise disjoint, we end up with the same integral. Okay, so this tells us that if we have a representation of a simple function, even though the coefficients are not distinct, provided that the sets involved are not pairwise disjoint, we can use that representation to calculate the Lebesgue integral of that simple function. In fact, this is the content of the following theorem. So we can generalize this observation as follows. And this is the first version of our independence with respect to the representation of the simple function. So let us consider phi, which is a linear combination of beta sub j times the characteristic function of e sub j where each e sub j is in sigma for j from 1 to m. They are pairwise disjoint. So for different indices j and k, the intersection of e sub j and e sub k is the empty set, and the coefficients are non-negative. Then this linear combination is a simple function, a non-negative simple function, and furthermore the Lebesgue integral is equal to, so we can use this representation as if it is canonical. So that would be the linear combination of the coefficients times the measures of the sets E sub j. Okay, so take note here that there's no assumption that the coefficients beta sub 1 up to beta sub m are distinct. Okay. Now, so to prove this, first, let us show that this phi is indeed a simple function. Well, that it's easy because this is measurable. Since E sub j is in sigma. So the characteristic function of a measurable set is a measurable function. Hence, phi being a linear combination of measurable functions is also measurable. It is non-negative because the coefficients are also non-negative. So it is a simple function because it is measurable and it has only a finite set of values. So to prove the second, that is the Lebesgue integral of the simple function can be calculated using this representation. Let us denote by, let's say, alpha 1 to alpha, say, n. Let this collection be the distinct values, be the set of distinct values among the beta sub 1 up to beta sub n. So obviously, the betas may have repetitions, so the number of distinct values is less or equal to m. And for each, let's say I, from 1 to n, let us define the index set I sub small I to be the set of all indices j such that beta sub j is equal to alpha sub I. So here we just collect the indices of the betas that correspond to or that are equal to alpha sub I. Then a sub I, this is the inverse image of alpha sub I, is the union of the e sub j's j in the index set I sub small I. So what you do is you just combine. So if this is alpha sub I, you just combine all sets e sub j that satisfies this property. So that is this union. And since the alpha sub i's are distinct, it follows immediately that this is pairwise disjoint. And from this, we can now write the canonical form, canonical representation of your simple function as follows. I from 1 to n of, let's say, alpha sub I times the characteristic function of a sub I. Okay, so with this, our goal is to show this. So let's start with the right-hand side. So if you take the sum, so j from 1 to m, beta sub j times the measure of e sub j observe that this, let's say, collection of indices, this one is a partition of the collection of indices with respect to beta. Since the alpha sub i's are distinct and you can be only equal to a unique alpha sub I for the beta sub j's. So if this is a partition, then we can partition the sum as well into two. So first you take the indices in I sub I and take the sum for all small I from 1 to n. So since this is a partition, the sum is precisely the same. So there's no repetition and you get all terms precisely one time. Okay. So here, let us express the inner sum. This quantity here so by linearity, if J is in, so there should be a correction in the index, this should be J. So if J is in I sub I, by definition, this is equal to alpha sub I. So we just follow this one here. So this is now independent. So I can pull out that. And we have the sum of the measures of the E sub J's, applying the additivity of the measure. So the sum of the measures is just the measure of the union. Okay, so however, we know that the union of E sub J, J in I sub I, is equal to A sub I. And because we have here the canonical representation of your simple function phi, we can use this in the definition to calculate the integral. So this is the Lebesgue integral of phi with respect to the measure mu. And that is what we wanted to show according to this theorem. So again, if you have a representation of your simple function wherein the sets involved in the characteristic functions are pairwise disjoint, so even if the coefficients are not distinct, you can use that to calculate the Lebesgue integral of your simple function. Okay, so here one might ask, is this assumption necessary? So in other words, can we drop this assumption? If I have a representation wherein, let's say, the sets are not necessarily pairwise disjoint, can I still use that representation to calculate the Lebesgue integral of my non-negative simple function? So in fact, that is the case. So this assumption can be dropped. And this will be what we will prove in the succeeding discussion. But before that, let us discuss another property, which is the linearity of the Lebesgue integral for simple functions. So non-negative simple functions. So consider two non-negative simple functions, say phi and psi, and two non-negative coefficients. Then the Lebesgue integral of the linear combination is the linear combination of the Lebesgue integrals. Okay, so to prove this, well, again, one can show easily that the linear combination is a non-negative simple function. Since the coefficients involved here are non-negative, so the linear combination is non-negative. And we already know that a linear combination of measurable functions is measurable. So therefore, the linear combination of two non-negative simple functions, as long as the coefficients are non-negative, is also a non-negative simple function. Okay, so for definiteness, let us write the canonical forms of these two simple functions as follows. So for phi, let's say it has n distinct values, alpha sub j, and psi has m distinct values, say beta sub k, of course, here the alpha sub j's and the beta sub k's are all non-negative. A sub j is the inverse image of the singleton alpha j, and b sub k is the inverse image with respect to psi of the singleton beta k. Okay, so from this, since these are the alpha sub j's are the values of phi, so if you combine all the inverse images with respect to these values, you end up with the whole domain. And this is the same as this one. So you do that also for psi. So this is basically the inverse image of the range of phi. So that is the domain of phi, which is x. And this is the same. So this is the inverse image of the range of psi. And that would be also the domain of psi, which is x. Okay, so let us define the sets C sub jk. So now we have two indices. So this is A sub j intersection B sub k. Then this collection is pairwise disjoint. In other words, C sub jk intersection C sub, let's say PQ is disjoint. So the intersection is empty for different pair of indices. So this follows immediately from this definition and the fact that the A sub j's are pairwise disjoint and the B sub k's are pairwise disjoint. So if these two ordered pairs are not the same, then at least one must not be the same. So for instance, if the first component, if the first components are not the same, then that would be the A sub j intersection A sub p would be disjoint. And that would give you this equality here. The same reasoning applies for k and q. If these two are different, then B sub k intersection B sub q would be empty as well. and you end up with the same conclusion. And here we can write the linear combination as follows. So it is now a double sum of alpha times the values of phi, which is alpha j, plus beta times the values of psi, which are beta k, times the characteristic function of c sub j k. So again, take note that the value of phi is precisely alpha sub j when you are in a sub j. And at the same time, the value of psi is the same as beta sub k if you are precisely in b sub k. So the value of the linear combination is precisely this linear combination of values as long as you are an element of the intersection of these two sets. So we can now write the linear combination in this way. So take note that since where should we write that? Since this is in sigma by measurability of phi, and this is also in sigma by measurability of psi, then this intersection is also in sigma. Since alpha and beta are non-negative, the alpha sub j's and the beta sub k's are non-negative. This is also non-negative. So here we have represented the simple function, that is the linear combination, as a sum where the sets involved here are pairwise disjoint. So we can use the previous theorem. So from the independence of representation theorem, the first version, we can use this representation to calculate the Lebesgue integral of this simple function. Carrying out that calculation, so that would be the following sum. You copy the coefficients and take the measure of the set. So we split the sum into two parts. So first, we can pull out these two coefficients. So alpha sub j, mu of c sub jk, but c sub jk is the intersection. So by definition, a sub j intersection b sub k plus beta. Here we interchange the sum, the order of the sum, and we will have a beta sub k times the measure of a sub j intersection b sub k. So here we, of course, pulled out the coefficients, alpha and beta, because they are independent of the indices of summation. And on the second part, we interchange the order of summation. So since this is independent with respect to the index k, we can pull that out. And we can also do that for the second sum. Looking closely at the inner integral, or inner sum, I should say, this one. So this sum so mu sub a sub j intersection b sub k by additivity of your measure. So this is the measure of a sub j intersection of the union k from 1 to m b sub k. So here we applied the distributive property of sets. But we know that this is the same as x from here. So the union or the inverse image of the range of psi, that would be the union, is basically the domain, which is x. So this is nothing but the measure of a sub j. In a similar note, the second summation, the second inner summation, after pulling out the coefficient beta sub k, would be calculated as follows. So again, additivity of the measure, this would be the union j from 1 to n of a sub j intersection b sub k. And this is also equal to x. Therefore, this is just the same as the measure of b sub k. Okay, so continuing this calculation here. So this is equal to, so using these properties, we now have so here is alpha sub j, and the inner sum, as we have said, is equal to the measure of b sub j. And you do that in the second sum. And you can recognize that this is equal to this sum as well. So now going to the fact that these are your canonical representations for phi and psi, the Lebesgue integrals of these simple functions for these representations would be precisely this one. So this is the same as the Lebesgue integral of phi d mu. And this is the same as the Lebesgue integral of psi d mu. So with that, we can now conclude that this is equal to alpha Lebesgue integral of phi plus beta Lebesgue integral of psi. Therefore, the Lebesgue integral of the linear combination is the linear combination of the Lebesgue integrals, which is our goal in this theorem here. With this, we can now prove our second version of uh, independence with respect to the representation of your non-negative simple function. So for this, you now have a linear combination, say gamma sub j, j from 1 to m, where f sub j is in. Okay, let us see the notation. So let us use the same notation. So let us use beta sub j here. But without the pairwise disjoint assumption on the sets. And here, beta sub j is non-negative for j from 1 to n. Then again, this linear combination is a non-negative simple function. And so therefore, I can calculate the Lebesgue integral. And the Lebesgue integral can be computed using this representation, even though the sets involved are not pairwise disjoint. So in other words, we drop the assumption that the sets are pairwise disjoint. So the proof is very simple. Since the beta sub j's are non-negative and the characteristic functions of E sub j's are non-negative simple functions. So applying linearity and of course induction, we know that the Lebesgue integral of phi, so phi is equal to the linear combination of the characteristic function of E sub j's with coefficients beta sub j. So you take this as your simple function and you take this as your coefficients. We can now apply the linearity of the Lebesgue integral for simple functions. So the Lebesgue integral of the linear combination is the linear combination of the Lebesgue integrals. And take note that this is already in a canonical form. We know that this Lebesgue integral here is equal to the measure of E sub j. And that is this theorem. So again, to compute the Lebesgue integral of a non-negative simple function, if you can write it as a linear combination of characteristic functions, it doesn't matter whether the values are distinct or the sets involved are pairwise disjoint. You can use that to calculate the Lebesgue integral of the simple function as if it was canonical. So to close this lecture, let us prove the fact or the property that the Lebesgue integral for simple functions is monotonic. In other words, if I have two simple functions, non-negative simple functions, wherein phi is less than or equal to psi, then the corresponding Lebesgue integrals satisfy the same inequality. So the Lebesgue integral of the smaller simple function is less than or equal to the Lebesgue integral of the larger simple function. So to see this, we can write, so the larger function as the sum of two simple functions. So here, so the difference of two measurable functions is measurable. Since phi and psi takes the ranges are finite, the difference has also a finite range. So this is a simple function having a finite range. It is, a non-negative simple function. Why? Since psi is greater than or equal to phi. So this difference is non-negative. With this, of course, by assumption, this is a non-negative simple function. If we apply linearity, so by linearity, we already we can obtain the following. So the Lebesgue integral of the sum is the sum of the Lebesgue integrals. And according to the definition, the Lebesgue integral of a non-negative simple function is non-negative. Therefore, this sum is greater or equal to the Lebesgue integral of phi, which is this inequality and reversed order. So therefore, the Lebesgue integral for non-negative simple functions is monotonic. And that's it for Lebesgue integrals of simple functions. In the next series of lectures, we will extend the definition to non-negative measurable functions, and then later to a more general class of measurable functions. So see you until then.